afternoon, ladies and gentlemen. So I have a big pleasure to introduce Bašič-Šiško from University of Rijeka. She did a PhD with Boris Moha in the University of Zagreb. Also together with another guy, Ivan Dražič. And she will talk today about real micropolar gas flow models. Please.
Thank you. Thank you very much for the introduction. It's nice to be here. So, as Shaka said, today I will be talking about this model. It was my PhD thesis dealt with this model and also some research I did after that. Okay, so I will first start by introducing the model itself, and then I will discuss some results which I proved for that model. So,
Now?
Okay, yes. Okay, so we're starting with the classical Navier-Stokes equations for the flow of compressible Newtonian fluid. So we have a certain equation of state which connects pressure and mass density, and we also have equations that stem from laws of conservation of mass and momentum. Okay, so we start with that, and in the model we are that I studied, we also took into account the effects of temperature, so we do not neglect temperature, and which means that we also have to consider an additional equation that comes from the law of conservation of energy. Here we have that equation where Q is heat flux and T is stress tensor with velocity is energy and rho is mass density. Okay, so with this we introduce some additional assumptions. First one is that we have the following relation between energy and temperature. That is, we consider our fluid to be thermodynamically polytropic, and also we assume that the Fourier law holds. That is, we have the following relation between heat flux and temperature. Okay, so that's the first part. We have temperature, that is energy equation. Next, we need to then adapt the equation of state we are using. So in the most usual choice of the equation of state is this one for the ideal gas. Which says that the pressure is proportional to product of mass density and temperature with the constant which is the gas constant. Okay, so in my research I did a step up also, so we didn't just look into this equation of state, but rather a more generalized case where we don't have just the product of mass density and temperature, but some product of some power of mass density and temperature. Okay, this equation of state is sometimes called real gas equation of state. So that's why we have this first part of the name of the model. So the realness comes from this equation of state. Okay, so that's the first part. Then the second part is micropolarity. So micropolar fluid is a generalization of the classical fluid model when, in addition to all the macroscopic effects that we are interested in, we also take into account some local micro effects. In this case, we take into account local micro rotations in the fluid while all the deformations are neglected. This model was introduced by Ehringen in the 60s, and it was one of the models of such type that in some way took into account the microstructure of the fluid, but it proved to be most successful of them all because it was simple enough to allow all the classical analysis, and on the other hand, it introduced enough novelty so there has been some improvement in modeling, especially for the fluids with pronounced particle structure, especially when the characteristic dimension of the flow is relatively small. Okay, so this is it. So now we need to see how we introduce this into our equations. So as it's written here, we introduce this microphenomena. We describe this microphenomena through a microrotational velocity vector, which we denote by small omega. And now we also need some additional equation. This equation is the law of conservation of angular momentum. So in addition to laws of conservation of mass, momentum, and the last one is for the energy, we have this third one as well. I mean, the law of conservation of angular momentum also has to be satisfied in classical fluid mechanics, but there, if I'm not mistaken, it's implied by laws of conservation of mass and momentum, and together with the fact that the stress tensor T is symmetric. Here, that is not the case, so we have all those micro inertia things that are happening in fluid, and we also will see in a moment just that this tensor T is no longer symmetric. Okay, so this is the equation. Now let's see what it's made of. So here we have a constant Ji, which is a so-called micro inertia density. Next, here G is some force, which is called body coupled density. And in our analysis, we usually take it for simplicity's sake to be 0. Okay, so as I mentioned, stress tensor T in the case of micropolar fluid flow has all the usual bits here, and also some additional bits that stem from the micropolar effects. Okay, in addition to that updated stress tensor T, we also have an additional stress tensor, which is denoted by C and called coupled stress tensor. And introduces stresses on micro level. Okay, so in these two constitutive equations, we also we have some new constants, which are coefficients of microviscosity. So we have a few of them. Also, when we introduce this new effects, we also need to see how we need to update the rest of the equations. So what needs to be updated is the equation of law of conservation of energy. So we need to, we have here some additional terms which contain micropolarity and stress tensor C, and also this axial vector Tx, which is here due to the fact that the x it's not trivial because T is no longer symmetric in this case. Okay, so this is the basic system that we are interested in. So in my PhD, during my PhD, I looked into this model, but I also extended it in one more direction. First, what we did, we analyzed this one and then the extended one. But now I'll introduce the extension now as well with all this together, because the results for that extended model can be easily reduced to the basic model. So just to keep it more simple and shorter, I will introduce the final addition to the model, which is reactiveness. So reactive fluid model is the one. So we study a model where the fluid mixture is a mixture, some kind of mixture of gas, of fuel and oxidant. That fluid undergoes a certain chemical reaction. In this case, we are interested in a simple one-step irreversible reaction, which is an example of that reaction is combustion, for example. So we have a reaction where fuel, in the presence of oxidants, turns into products. So to describe the dynamics of this of this, we need an additional equation and also an additional variable. So we introduced z. It stands for the mass fraction of the unburned fuel, so it's some kind of percentage. Okay, and we also have this equation that tracks the changes of z and describes this dynamics. Okay, we also have some additional constant. So this is sigma is the fusion conditions, and we also have an additional function I, which is the intensity of the chemical reaction. Yes. So we have this new equation and the new unknown variable. Okay, so again, like with micropolarity, before we move on, we need to see if this new addition affects somehow the rest of the equations. So we all now, as well as before, need to amend this equation that comes from law of conservation of energy. We need to add this bit, which represents the influence of this chemical reaction happening within the fluid to the change of energy. So we have an additional equation, additional variable, and once more amended energy equation. Okay. What we need to briefly discuss yet is this function of intensity I. Usually in applications, it comes in the form of Arrhenius law, which is this function up there. But in our research and analysis, we wanted to incorporate a bit more general case. So the intensity function that we are interested in is of this form. So we have this z, the amount of unburned fuel, to some power times some function I tilde, which has these properties which we needed in the proofs, and which we consider not to be too restrictive, because this Arrhenius law satisfies all these conditions for the function I tilde. Okay. So now, taking all this into account, we can now get the full system, where we took everything into account, even the strength tensors, and the full system is this one. As you can see, there's a lot of it. In my work, I didn't do anything with this in 3D. What we we're looking into is a one-dimensional model version of this. Okay, so one-dimensional model written in the Lagrangian mass coordinates is written here. So we have 5 equations, and we supplement it with corresponding initial and homogeneous boundary conditions. Those are homogeneous Dirichlet conditions for velocity and micro-rotational velocity, and Dirichlet and Neumann boundary conditions for temperature and mass of unburned fuel. And in the following, we are trying to prove some results on this model here. So what we try to prove is the existence, uniqueness, and long-term behavior of the solution to this problem. So first, we define what we consider by solution. The solution to this problem, we are calling it generalized solution, is a set of functions that belong to the spaces that are written here. Of course, these functions need to satisfy equations and boundary and initial conditions. Also, due to certain embedding theorems, we have that a function that satisfies these conditions from the definition also belong to these a little more, let's say, prettier spaces. Okay, so this is our generalized solution. Now let's see when does it exist. So we proved several results in this order. So we first proved that the generalized solution to this 1D case exists on some small enough time interval, so we obtained so-called local existence. Next, we proved that this problem admits at most one solution, so we have uniqueness. And then we also obtained the global existence results. And this was in two phases. So first we obtained the so-called global existence on an arbitrary but finite time interval. And after that, recently we also got the existence on an infinite time interval. Okay, all those results we obtained for these assumptions that are written here. So we have some assumptions for the initial data. Rho 0, theta 0, and z0 are h1 functions, and v0 and omega 0 are h01 functions to be in accordance with boundary conditions. What we also ask of our initial data is that not to be vacuum or absolute zero. So we want there to exist some positive constant m0, which bounds initial mass density and initial absolute temperature from below. So they are strictly positive. Okay, and of course, to be in alignment with its physical meaning, this z is some kind of fraction of mass, so it's some kind of percentage. We need it to be at the start to have values between 0 and 1. So that's a logical assumption. And using for these assumptions, we can prove the existence of the generalized solution. But in addition, we can also prove that such generalized solution also holds somehow these initial assumptions. So the temperature on the whole interval of existence remains strictly positive, and also what is somehow physically necessary for physical interpretation, but this z also remains bounded between 0 and 1. Okay, so this is the brief overview of the results. Now I will go into a bit more detail. So this is the theorem on the local existence, and it says pretty much what I just told you under these assumptions that I explained a little bit earlier. There is some small enough time interval t0 where our generalized solution exists, and it has these additional properties. So to prove this result, we used pretty much standard technique. We defined a sequence of approximate solutions, which are where these coefficient functions are the solution to this ODE system of equations. So the goal now is to prove that this sequence is convergent, at least it's some subsequence, and the limit of that convergent subsequence is the solution to our problem. Okay, so we have these functions Vn, omega n, theta n, z n, and rho n defined in this way. Now we proceed to obtain multiple a priori estimates for these approximate solutions using some unknown, very famous inequalities. For example, we use Poincaré's inequality, and if we look into those approximate functions that we had, we can see that, for example, V and omega do satisfy the assumptions for the Poincaré and Ladničenskaja's inequality, but not the other two. So, so Z and theta do not satisfy none of these conditions. So the first kind of estimate that we needed to obtain is the one that will stand in place of those classical inequalities. So we got some version of them, which again connect the function and its derivative in this way. So using these estimates, we can then approve a whole series of these a priori estimates. and somehow the final one that we get is in this form. So we prove that there will exist a small enough time interval t where this bound for the approximate solutions hold, where this constant c is independent of n, which denotes different approximation levels. Okay, so we have these estimates. From these estimates, we can conclude the boundedness of the sequences of solutions, of approximate solutions in certain functional spaces. And then using classical theorems on compactness, we can obtain convergent sum sequences in the corresponding spaces. Okay, so we get these convergences for a row n and these for the rest of the functions. Okay, so now that we have a convergent sum sequence and its limit, it remains to prove only that the limit satisfies the equations and the initial and boundary conditions, which we did, and we obtained the local existence result. Okay, so somehow pretty classical. Next is the unit result. So we show that, and whichever time interval, our problem admits at most one solution. The idea of the proof is again quite classic. So we assume that there are two solutions. Then we look into the differences of those two solutions. We construct this approximate system that is written in terms of these differences between the two solutions, and then using the system we obtain some estimates that finally result in something like this. And then using Gromov argument with Gromov inequality, we can easily come to a conclusion that all these differences u, v, omega, beta, and z, where u is a volume, so it's 1 over density. It showed to be easier to look into 1 over a row than row for some reason. So we looked into that in that way for the system. All these functions need to be 0, so we get our uniqueness. Okay, so this was that. And now for the global existence. First, I will tell you a little bit about the global existence result on an arbitrary but still finite time interval. So we can choose any finite time t and prove that our problem has a solution on the interval from 0 to that chosen t, which still satisfies all these properties. Okay, with the same assumptions on the initial data. Okay, how did we prove that? We chose some capital T, our time existence interval size. Then we proved some, again, estimates. We have two key moments in this proof. So first one is energy inequality. We call it here generalized energy estimate. And the second important ingredient is so-called generalized Kazhikov representation of mass density. This representation of mass density enabled us to obtain a series of estimates that uniform estimates for rho and also theta, and then to get all the desired boundedness. Okay, so using these two main ingredients, we can get results. Some of them are written here. So we get, for example, boundedness from below for theta, then boundedness from above from theta in in this way, and after that, we can obtain uniform estimates also for rho. Okay, so using this this representation. The key here is that these constant speeds can they depend on the capital T. Only the estimates for so this constant C that appears in the generalized energy equation, I think that one does not depend on T, but everything here in the generalized Šiško representations or the constant that stem from that will depend on capital T. Okay, so using these estimates, we can again obtain some similar results, where again here the C can depends on the initial data and capital T. Now that we have these equations, we can obtain the existence result for of our solution on a chosen time interval from zero to capital T, because we have a local solution, and using these arguments we can extend it to the desired. Okay, so this was the first version of the global existence result, and later, so after my PhD, I also got this result where we managed to prove the existence on an infinite time interval. So it's under the same assumptions, and the proof is not too much different, but it's a bit more technical than the first one. So we proved that under the same assumptions, we have the solution on infinite time interval that satisfies these inclusions. Okay. How to prove that? Again, a series of estimates. We want to get something like this written here. It is somewhat similar to what we have before, but the key is, of course, that this constant C at the end does not depend in any shape on time T. Okay, so as I said, we have a lot of similar things, but some of them are more complicated, just technically more complicated, and then we were able to get these time-independent estimates and then conclude the existence. Okay. And finally, together with this infinite existence on an infinite interval, we also managed to conclude something about the long-term behavior of the solution. So we concluded that it's for large times it stabilizes around the stationary solution with some rate. That rate is in some cases exponential, and in other cases we only managed to obtain some kind of power decay. The here parameter m that we have the differences of the decay rate. That is, if you remember, the parameter that was included in the intensity of the chemical reaction. So if we have just micropolar gas model, so without reactivity, we actually have exponential decay. But if we have that reactive model, and if m is strictly greater than 1, then we only manage to prove power decay. Okay, this is also some excerpt from the proof. Again, quite technical, which enabled us to get this kind of result. Okay, so this is somehow conclusion of the part for the, let's say, true 1D case. What we did more recently was we also looked into a more expanded case, let's say, which in the end, again, becomes just a 1D case, but again, a bit more complicated. So we looked into a spherically symmetric solution on a domain which is part of the space between two concentric spheres. So we have that kind of domain, and we have an assumption on spherical symmetry of the solution. Using those assumptions, we can write all the elements of the system, so the stress tensors and all the rest of it, in terms using those assumptions and including that into the equations. What we get is this kind of system. So this spherically symmetric case, I only looked into when for the non-reactive model. So I don't have the Z part of it. So it's only micropolar real gas model. But for this spherical symmetry here, we have the model written in Eulerian description, and here it's maybe visible because later I have it also in the Lagrangian description. Why we use Lagrangian description? Because in this case we have much simpler first equation. So equation of continuity. Okay, so we have, this is the case in Eulerian description, and much simpler, of course, in Lagrangian description, which enable us to get all kinds of stuff and make the analysis more simpler. Okay, so we looked also into this case a bit. So all the strategies, everything is pretty much very similar to what I explained before. Just again, we have more terms. It's just a bit more complicated than before. So we obtained all the similar results, not all of them, but some of them for now. So again, we have a similar definition of the generalized solution, and the theorem on existence of the solution. So we proved that the solution will exist on an arbitrary but still finite time interval. We didn't prove anything yet for the infinite time interval. Okay, so we have this result. As I said, the proof of existence is quite similar, again in two phases. We first have a local existence result and then the global one. It goes similar way. So we have first Pareto-Galerkin approximations, then we get all the usual a priori estimates, which are now, of course, much more complicated, more to do. Okay, so using these a priori estimates, again, in a similar way, we get the boundedness, the convergent sum sequence, and conclude the existence on some small enough time interval. And then when once we have local existence, we can then similarly prove the global one on arbitrary time interval t. So for that, we again use the similar ingredients. First, we have the generalized energy estimate, which again, just a bit more technical, has these R's appearing everywhere, but still quite similar. Here you can see some of the technicalities we have to deal with. And of course, similar to that, we have generalized Kajikov representation, again, a bit more complicated, but still pretty much the same. Now using this representation, again, we can obtain uniform bounds for theta and rho, and then conclude all the other estimates, and finally get the result. Okay, so pretty much the same, but just up to some technicalities. Okay, these are these estimates again. Okay, so finally, I also wanted to just show, because this proof of local existence, it's in a way constructive. So we have that Pareto-Galerkin scheme, which ends up as some ODE system, which we can then solve. So we didn't use anything very fancy. We just used those approximations. So solved that ODE and got our numerical solution, just to see that the things work as expected. So we chose some relatively simple initial data and all the coefficients. This choice of coefficients is most physical. It's as far as I know, there's still not very much physically valid, I think, coefficient, especially the parts that related to micropolarity, so the microviscosities and the like. So we chose some numbers just to see what's happening. So we got something like this. Here we have represented mass density rho. We can see for larger t's, it really does stabilize around 1. And for velocity and microrotation, we can see if you look at the scale, they go to 0 relatively quickly, especially micropolarity, and temperature also stabilizes around some constant. Okay. And what we also found interesting to maybe display is the solutions for different values of the pressure exponent P. If you remember, this real part of in the name of the model refers to the pressure exponent, different pressure exponents in the energy in the generalized equation of state. So here we solve the system for a couple different. For several different values of P. So P is equal to 1. That is, we have an ideal gas model. This is the blue triangle line on the graphs. And then we also have P is equal to 1.5, 4, and 10. And we can see that there are some things that we can notice. Of course, this is just one example, but in the few examples we looked into exhibit some similar behavior. So we have some so for larger pressure exponent rho, so mass density stabilizes somewhat quicker to 1 than when the pressure exponent is greater, and some similar conclusions can be obtained for also for absolute temperature data. Okay, so throughout my PhD and after it, I was supported by different projects from Croatian Science Foundation and University of Rijeka, so I would like to thank them. And thank you very much for your attention.
Thank you very much for the nice talk. So now I am opening